It is my pleasure to introduce our next speaker, Dr. Robert Cox, the leader of the AFNI group. And if you would all please give him a warm welcome.
I thought warm might mean throwing things, but I guess not. So I'm going to spend some time talking about AFNI and multimodal imaging capabilities within AFNI, but before that, I'm going to give you some sort of general background information. And before I do that, I'm going to warn you that everything is complicated, right? And so almost everything I say will be some sort of horrible simplification, and some of it may simply be wrong, for that matter. But I think this Dilbert cartoon explains the process fairly clearly. So I'm going to start with the sort of ruminations that I talked about, which ruminations literally refers to the rumen of a cow. It's what a cow does, sort of sit there, chew things, and digest. So, but I think that I'm not going to be actually doing that, but I will be thinking philosophically like cows are surely doing. So the origin of AFNI, as I moved to Milwaukee to get married, and then I got somehow roped into this then newfangled fMRI stuff. Within a year or so, I sort of had this, after frantic learning like what the brain is and stuff like that, I started to realize that sort of the things should be done in 3D. The brain, I mean, the fact that we gather slices in 2D, whoosh, doesn't mean that they have to be analyzed or viewed only in 2D. And so, but everything should be done in 3D. And at the time, everything was being done in 2D. And so that was the start of AFNI. So that was summer of '94, so that makes it 25 years ago. And it worked out pretty well, actually. I didn't expect it to happen like this, but it did. AFNI, by February, I reached sort of a place where I felt AFNI was actually useful for several things, and then I put it on an FTP server and announced it to any email list that was relevant to brainology that I could find. Actually, the term open source was introduced in '98, although there's a fair amount of argument about who actually originated it and when. Before that, they just said free software. Open source was like a marketing thing, so that companies with free, who trusts anything free, but open sounds good. But why did I give AFNI out to the masses? That's been asked to me several times, actually. Some of the people at MCW wanted to keep it, so they would have the advantage of having AFNI for themselves. And some people said, why don't you start a company like Rainer Gruber did? But I'm not I'm not an entrepreneur unlike my father. It's not my personality. And why did I give it out to the masses? Because I wanted to give back. It wasn't in my real interest, maybe in the interest of a user to keep it private, but it isn't in my interest to keep it private. I wanted to give back. I've benefited a lot from other people's contributions to various things, and I wanted to give something back, whatever it is. So, switching to philosophy or whatever you might call it, in fMRI land, there's this thing that comes up a lot. Not universally, but it comes up fairly regularly, which boils down to this is a parody of it or distillation of it, is someone saying, my method, this method I'm proposing to you right now is the best, and not only is your method worse, your method is wrong, and everything that was done with it is wrong. I've heard this many times over the years. Most of the time, the differences between the tools and methods that are being contrasted are not as huge as people say, and they're not that well documented or explained in most cases, although with the rise of openness that at least people can put their programs and their scripts out on the web, which didn't used to be the case, even like 5 or 6 years ago. But they often not tested on a wide variety of data sets. And of course, sometimes that method that people use is actually wrong or perhaps incorrectly implemented. And an example of that is something that I, like about 6, 7 years ago, I sort of came to realize that a lot of people were doing the following. They were doing for resting state fMRI, they would bandpass their data, so to remove the frequencies of no interest, the high frequencies, say, that are not thought to be bold effects. So now they have the bandpass data, and then they would apply other they would project out other regressors of no interest, like the motion parameters and stuff. This is wrong. This is not inferior. This is dead wrong. And people had published a lot of papers doing that. It never occurred to me that people would do that, because from a point of view of a mathematician, it's insane. It's wrong, because you will introduce back into you could A then B is not B then A. You do it in one different order. You can do it in different order if you're careful. But most people weren't careful because they didn't understand it. That's wrong. And pointing out that that was wrong was a good thing. How badly it affected the results, that's a different story. So some things are wrong, but this isn't physics. Physics, the radar, I used to work in radar, so you know what electromagnetic radiation equations are, and so you can figure out reasonable approximations for what bounces off an airplane and comes back and stuff like that, and be sure that you're as right as you can be. We don't know how the bold effect works. We have some idea, of course, after 25 years of thinking about it, but we don't really know how it's intermediated or what's a reasonable model for it or anything like that. So much less its connection to the neural stuff. It's not physics. It is, everything's physics if you go far enough down, but we're so far away from physics here that, which is my background, that there we are. There are these are the ones that I could come up off the top of my head, and I'm sure there are a few more. Some big controversies, the kind of thing I'm talking about, where people say everything is before me is wrong. The first one I can remember was, I'm not going to give any names to go with this. If you're in the field, you may be able to attach a name to these. But was stimulus correlated motion artifact. In every one of these cases, what they were bringing up was a valid point. And then they amplified it, turned it up to 11. Okay? And stimulus correlated motion artifact. It's a real effect that if a person moves their head, I show you a picture of a puppy, and you say, "Oh, that's nice." And I show you a picture of a hideous spider, and presumably the amygdala does something like that. But you may also flinch because you don't like hideous spiders. So there's motion correlated with the task or the stimulus, and so that's going to, of course, motion is going to cause signal changes. So that's going to cause things that look like goes up and down or down and up. So that's a real artifact, and it's an important thing to try to allow for in the data. However, the author of this paper went on to say, I don't think fMRI means anything. The bold effect doesn't exist, or it's too unimportant. Everything that's been published is stimulus-correlated motion. I think retinotopy makes that hard to believe, right? It's hard to imagine how you move your head to create retinotopy in the calcium sulcus. But, so it was a valid point, and it was oversold. Let's move on to, I'm not going to discuss all of these things because we'll be here for the rest of the century. There's, let's say, voodoo correlations. Anyone remember that one? So voodoo correlations, again, is a valid point. That is, by using this fMRI data to extract the boxes only of interest, the ones that are above some threshold, and then use the same data and correlate that with, say, subject's nose length or some other parameter about the subject. That's semi-circular reasoning, because you're selecting voxels that already passed one threshold, then you're doing something going another threshold, but you're treating the statistic on the correlation coefficient of the second step as if it was a single thresholding step. And that tends to exaggerate the correlation, so that a correlation that might have been, if you used independent data, 0.5 might come out as 0.7 or something like that. Again, it was oversold. Because first of all, the guy in this paper had these simulations showing this occurs in just random data, but if you look closely at it, he had to run it only occurred like one time in a few 100,000 out of his simulations, which isn't, if something only happens one time in 100,000, we all drive to work or something like that. the odds you're going to get killed are about the same, right? So again, it was an important point, oversold. 2016, the great cluster panic. Remember that paper about saying, I mean, it had it in it, calls into question everything that's ever been done in fMRI, which then they had to retract because shitstorm landed on them, right? Again, a valid point, oversold, and so on. You know, can't we just get along? Remember Rodney King? He said, can we just get along? Not can't, but can't somehow seems better. Of course, I have my own rather strong opinions about a number of things that are done in fMRI or have been done. Global signal regression, in my opinion, is not a good thing, for example, because you're interested in the signal from gray matter and you want to project out artifacts. But if you use the gray matter signal to derive the artifacts, you're going to be almost certainly, unless you're extremely clever, be regressing out also some of the thing you're looking for, which will change your results in ways that are essentially unpredictable, especially when you're doing it between different groups of people, like patients who may have more motion and controls who may have less motion. The artifacts will be different, the projection will be different, and you can end up with group differences that are statistically spurious. That's my opinion. Global pre-whitening, using the same pre-whitening or technique for allowing for temporal correlation in fMRI, I think this is inferior to Vox. It's easier to do because you only have to do it. You have to do it once, not several 100,000 times. But it's inferior because we don't just take the data and process and pre-whiten it in the analysis. We do a bunch of other previous steps first, including interpolations and smoothings, and those introduce correlation in time. Even smoothing in space introduces correlation in time, which is not intuitively obvious, but comes from the fact that things are correlated in all directions in space and time. And the result is, and the correlation comes from, some of it comes from breathing artifacts. I mean, in fact, it's hard to get your subject to stop breathing in the scanner, or at least they'll object. And so the result, and that's very spatially dependent. So the temporal correlation is very spatially dependent. And so if you do it voxel-wise, you can allow for that. And in our recent work, we've actually been, something that's on the previous slide, the stimulus is fixed effect fallacy. We found that this is very important. It makes a big difference. We're starting to work on that, and we discovered that this is very important. But I don't say this is bad. I say it's inferior. I have different levels of opinion. Resampling data without recomputing the spatial temporal correlation used to do the correction of statistics is bad. And I mention this because there's a well-known software package that does this, and their statistical results are, I think, not checking every participant's data for quality and just throwing it all into the group analysis or something. I think this is real bad. And someone very famous, relatively famous anyway, told me that, well, we have too much data to do this for. But we have so much data that it'll all average out. I couldn't even begin to answer that, actually, except to say he's nuts. These are my opinions, remember. Believing DTI tractography literally. Well, DTI tractography is pretty interesting, but is it bad or good? I don't know. I'm like puzzled by this because it isn't really literally true, but it has some correspondence with reality. But people should understand the limitations. And blindly trusting software, even AFNI, is bad. That's got red stuff around it to indicate that's actually pretty damn bad. I'll tell you a story which has nothing to do with AFNI. A friend of mine used to be as a structural engineer, and he was hired to work on to be a head of a project designing piping supports for a nuclear power plant, the Chicago Midland plant, which was never actually built. But they have a lot of pipes in a nuclear power plant. And so they have thousands of supports. They have to hold up the pipes, and they have to be designed against various criteria like earthquakes and overloads and safety factors and so on. And he came in halfway through the project and decided he wanted a review of, are we really halfway through? And he had like 20 engineers under him. He pulled a random sample and found a lot of them were dead wrong. I mean, so wrong that you can't believe it. Like, this thing would, they calculate the deflection in, how much it gets deflected in angle. You have a cantilever, say, something that's holding the pipe. It gets deflected, and, that might be 0.001 radians in normal situations. They have things like 3 radians, which is, halfway around the circle. You don't think the pipe support should go like that, because it's probably beyond the accuracy of, or the stability of anything. And but the engineers writing this had just believed the software and just stuck it in. And fortunately, they didn't build the plant, but he got in a lot of trouble with his bosses for moving it from 50% complete back to 20% complete. There were plants built like that in the Northeast, and they all had to be shut down and have their piping supports individually examined and rebuilt, and it cost hundreds of millions of dollars. So don't blindly trust software, even my software. And I'll give you another example, a real one, image registration. There was some data I downloaded several years ago from people who are very good, and I have a lot of respect for, and they had registered, used another software program, not AFNI, to register their data as an MNI template. 2% of their data was 60 degrees off, not a little bit off. I mean, I looked at it and go, what the hell? They had like that. Supposed to be like that. And I sent them an email and said, you should probably look at this and do this again. And they did. But they had trusted FSL, which, said who it was, which Steve Smith once told me, FSL never makes a mistake, since I mentioned the name. Which made me think that he's either some sort of weird British sense of humor or he's mad, which, of course, are not mutually exclusive. I have a lot of respect for Steve Smith and what he's done, but nothing is perfect. And then I was moving from opinions to grumpy old man. I turned 65 this year, so that I'm legally a grumpy old man, grumpy old white man, I guess you could say. I really dislike certain terminology that's been promulgated. Functional connectivity to mean resting state correlation, or effective connectivity to mean something that sort of seems like it's causal. These terms are using secondary definitions of the words functional and effective in the reason they're used. But people, of course, when you see the word function, they think this is like the brain. This is real connectivity, not just that. In some sense, these things are correlated, which I think is misleading. At best, I would call it these things correlativity, which isn't really a word, but it should be. And of course, there's overhyping and overinterpreting. I gave some examples of that, which they were overhyping things that were real and important things to point out. All of those things a couple of slides ago. Here are some things that are just, in my personal opinion, are just nuts. I'll remember my PhD's in mathematics, not neuroscience. I know the brain is up here. I'm almost certain of that. Something that I do dislike intensely is the widespread use of 2 one-sided t-tests versus 1 two-sided test. We published a paper about that recently. I think it's just verging on statistical dishonesty. And using techniques without understanding. I mean, no one can understand everything. The world is too complicated. I don't think there's anybody in the world that really understands how a computer works all the way from, there must be 50 layers of software and hardware. I don't think anybody can understand more than a few of those, but you need to understand something about what you're doing or have someone to ask, because otherwise people just blindly use the software. And I feel really sorry for people that are like isolated neuroimaging people somewhere, that they had downloaded the software and they don't really have any. There's like 3 of them, and that's all. And I feel sorry for them, but they're going to have a hell of a time unless they're like all geniuses, which is rare. I mean, people should stop saying everything's wrong because they didn't allow for this effect, which I just noticed. It's unlikely that everything's wrong. I mean, I'm exaggerating, of course. People don't say everything's wrong, 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 but they kind of imply it. People need to describe the methods used in the algorithms very clearly, because people would write stuff like this, bandpassing. We bandpass the data and regress out stuff. Unless you saw their script, you wouldn't know that they did it wrong, because it's just it's a phrase in their method section. Method sections don't need to be infinitely long. Now we have online supplements. And, but even open source code is helpful, but it's, everyone knows software can be opaque. Read software I wrote a few years ago, and I said, who wrote this thesis? Who wrote this? And then I said, oh, well, obviously that was me, because no one else has ever touched this file. But it would be nice to have some humility. But of course, in our modern society, we value people, we exalt people who talk with absolute confidence, right? I mean, it's, I can do this, you can't do this, And I'm slowly beginning to realize that anyone who talks with absolute confidence should immediately be ignored. So that was all the fun stuff. Now a description of why you should trust AFNI implicitly. So I'm going to talk about some of the AFNI features that are relevant to the meaning of this conference. I'm just kidding on the trust AFNI implicitly. So AFNI was at first for just dealing with fMRI data time series coupled with the T1 weighted structural scans. This little movie is just for fun. It's a way we use to check the alignment of the the T1 and the EPI, but it also just looks fun. It had the time series regressions per subject and voxel-wise t-tests, for taking the results of that, the so-called two-level analysis, producing, a group study, all in 3D, of course. So the arrow time moves forward. That was when I was in Milwaukee. I moved to the NIH in 2001 when the NIH started buying fMRI scanners, by the dozen, well, not that many, but a bunch, which is an expensive thing to do, so they needed data support. And so I was able to hire people to contribute to AFNI. And so we can now handle more types of brain imaging data. The data can be defined over 3D grids or 2D surfaces or on random point sets. I'll give some examples of that. Many of our analysis codes are agnostic about the underlying data geometry, or using the technical term for mathematics, the domain of definition of the data. And the reason for that is things that don't involve spatial computation, things that involve simply like regressing a time series or something, it doesn't really care where, here's a time series, there's a time series. The geometry is unimportant. For smoothing, of course, geometry is extremely important. So it depends on that. That's why I say many, not all. There's a long example, but I'll go through it quickly, about the mixture of diffusion, DTI tractography, and resting state fMRI. Resting state is a self-referential thing. It's not tied down to something external you know or measure about the subject, like the reaction time or simply the task times. That's an external object thing, when you flash the picture of a face on the screen and when they press the button. And resting state is purely self-referential. It should trust it, in my opinion, needs to be tied down to something else. Then there are a bunch of something else's that it can be tied down to, but one I'm going to illustrate here is white matter tracks that come from diffusion tensor imaging. So here's a naked brain surface. All this stuff you're looking at is in SUMA, which is a part of the AFNI package. So here's the resting state correlations from a seed. So the seed is given by a little yellow dot there. And if you click on that seed, after setting the software up properly, it computes interactively. The mouse click computes interactively the correlation coefficient of the seed voxel time series with every other node on the surface voxel time series, and it thresholds it and colorizes it. And we call that instacore because it takes longer to explain than it does to happen. It takes about basically video refresh time to do for hundreds of thousands of voxels. Computers are fast these days. So that's fun. Well, here's the DTI tracks, all of them that on the surface of the brain. Well, except that you saw the previous slide, you wouldn't know there was a brain there, right? This looks like a great wig, but it is not really informative. It is too much. And then if we put those two things together, well, you know, I mean, our brains aren't big enough to handle this brain. So one way then is to restrict the DTI tracks that only come from the seed, that only pass through the seed region. The seed region is a little hard to see here. The seed was that voxel or node there. The seed region for the DTI tracks, or the pass-through region, is this 20 millimeter radius sphere. I think it's 20 millimeters, something like that. Sphere, so or ball. So anything that white matter packet that passes through there is capped. The others are hidden. That way, you can see just a few of them. And now we can mix those two things. We can overlay in SUMA. All this is interactive. The DTI tracks that pass through the seed region and the time series correlations. But now the brain is in the way. You can't see the tracks or down in there. So we can open the brain. This is called the walnut brain, for fairly self-evident reasons. If you've ever seen a walnut, anyway. And so now this is the seed region in the space, the real space of the brain, but the image of the brain has been moved aside, and so now we can move along here, along this gyrus, and we can see as we move the seed voxel is node is here. But back in original space, that is that's where it really is, and then we see the tracks in original space, and we see on the surface we see where the correlations are, and we can move through this just by clicking. That's how I produced these slides, and trying to click relatively regularly as I moved along the brain, and you can see. So, for example, there's one where there's less color, so it's a little clearer. Like here's the seed, right? And that's correlated a lot with the stuff on its own side, and then on the other side there's a lot of correlation. And you can see the tracks that pass through the corpus callosum, I suppose, like this. But there's little tracks that go to other places. But so some of this is really connected. Some of this at least agrees with the DTI estimation of physical connectivity, which is reassuring, and some of it isn't, and which is still, it doesn't mean it's wrong. Neurons actually talk to more than one other neuron, so it can work past its way through. This is actually fun, though, shockingly. So we have this interactive exploration of these high dimensional complex data sets, and some of this stuff in AFNI can be applied to individuals for fMRI mapping of pre and post surgical if someone had a tumor removed, for example, resection, or ECOG. I'll show you some of that. Planning for deep brain stimulation, and I won't show you this, but AFNI can take data in real time and beat on it with a stick and send the results of the beating back into the subject for feedback. So I'll skip this surgery stuff because of time. Here's some stuff from using connectivity for deep brain surgery planning, where this comes from Helen Mayberg's group. You can see this is from the CT, which has been registered to the MRI, and then the traxography. This is you click on a place and you see the tracks that go through a region near that, and they use this as part of their decision of where to implant the electrode strip, because they feel it needs to be connected to certain other regions. And there's a software package which isn't written by us, but is written in cooperation with us from the NIH, called DBS, Deep Brain Stimulation Proc, which is available now for doing this. This is from some people in NINDS, as you might imagine. Here you can see that they mapped which contacts, the stimulus contacts, they put in this strip of multiple contacts, right? And were actually effective versus those that didn't have effect on whatever it is they're doing surgery for. And just blow that last picture up because I think it's. This is displaying that geometrical information in Summa, that information of good, of active, of useful and not useful, and this is in AFNI and cross section, both of which are helpful, I think. ECOG examples. There's a software. Let me go back. There's a software package called Alice, which was written with a little bit of our help, and they integrate Alice. Alice comes from Utrecht in the Netherlands, and there's a paper about it. And Alice is basically for processing ECOG data to put it all together so you can look at the ECOG data on the brain surface. And so this is part of the steps of making sure that you've got everything lined up and right. And the other thing that we have is, it's not, I don't know if you can call it multimodal neuroimaging. It is in a sense with macaques. There was an extensive study here for years on white matter tractography in macaques with viruses, right, labeled viruses by Karabacha Salim and others, of course. And then you can look at that now, the results of that in AFNI by, you get a matrix of what, when you click in some place, what is connected to what other named regions, and you can see the mapping of what is connected to what other regions, and so on. Of course, this is in the macaques. And recently, we've worked with Ted Uston, also at NIH, to register and display his 2-photon imaging data on top of the Allen Brain Institute's data. So you can look at those things in conjunction. And then this is the display in Summa, the 3D projection, and this is the slices in AFNI. So I wanted to spend a few minutes talking about something that doesn't have cool pictures, cool, colorful pictures, which are all, of course, all fun. But I want to spend some time talking about this next two slides, really, which are near the end of my talk. And that is our group analysis software, which, again, is running not voxel or node-wise, doesn't really care about geometry. And the first thing I'm going to talk about is multivariate group analysis, where the measurement for each subject at each node, for each condition, is not just a number, it is a vector of numbers. It could be multimodal data, or it could be multiple regression parameters from a single time series. And the user supplies a linear model in the format of the R language for specifying statistical models. And you can allow for covariates at the condition level or the subject level. And it sounds simple. It's not simple because it's got a lot of flexibility and a lot of power, and it can be used for all sorts of things. Besides being used on fMRI data, it could be used if you package the data up and build the right model. It can be used for mixing different data types together. It's a very general tool, and like general tools, it generally requires skill to use. But it is something that I think more people should be aware of because it can fit their needs. And if it doesn't fit their needs, one of the things is that we are really open to changing our software in ways to help people if it doesn't fit their needs, assuming it's not a tremendous amount of work. We were approached once to do FNIRS data, and we decided that was a tremendous amount of work, and so we didn't do it. But something like this, where you've already processed the data for each subject and boiled it down into some sort of vector of multiple measurements at each location, this is the kind of thing, if it doesn't fit what you want, maybe it can be beaten into submission. So that we get a lot of we get some requests like that, but often we just end up hearing people grumbling it doesn't do exactly what I want, but they never asked us, can you make it do what we want? So I'm advertising that. And another approach, which is relatively newer, the other one, the multivariate stuff goes back now 3 or 4 years, ancient history, is a Bayesian analysis. This is very computationally intensive. So it doesn't work, you can't work on every box on the brain, but you can work on hundreds of ROIs, or if you have ECOG data, then hundreds of nodes. And to fit linear models, we have a couple of software packages for that. And one of the strong advantages of the Bayesian approach is at the end you have a posterior distribution. Say you're estimating, like in 20 ROIs, then normally you have the multiple comparisons from 20 different tests. You have to say I have to allow for that. The Bayesian gives you a posterior distribution. The Bayesian simulations give you a posterior distribution in a 20-dimensional space of all those parameters. So, so if you project down to one parameter and say and draw its marginal posterior distribution, and then say, okay, I want the 95% box, minimal size 95% box. That's valid without any multiple comparison correction. Bayesian approach depends on priors. The priors can be thought of as a way of introducing regularization. Regularization, I think everybody's heard of, although they may not have heard that term. Lasso regression, for example, if you've heard of that, that's a form of regularization. So basically, ridge regression, or Tikhonov, it all goes back to Tikhonov, a Russian mathematician, which puts soft constraints on things. It doesn't put hard constraints, saying this must be less than 3. But it says once it gets bigger than 3, that's we're going to object unless the evidence is really strong. So that's what the Bayesian approach can be thought of as, and it's a systematic way of doing it, as opposed to an ad hoc way. And if you use weak priors, that is weakly informative priors, then it puts sort of weak constraints on the data, but does put constraints on the data, which makes problems that are otherwise unstable stable. That's what's one of the functions of regularization. And this has been applied, besides the fMRI data at the NIH, to zebrafish brain imaging data, multiphoton zebrafish brain imaging data, which, frankly, I have to tell you, 25 years ago, I wouldn't even have dreamed of that, besides I'd never heard of zebrafish. And to some neural recordings from monkeys, which I've actually heard of that 25 years ago, but I didn't ever think I'd be working with it. So finally, here's the floating heads of the AFNI group. And they did all the work, of course. I just take credit for it. And finally, here's some multimodal brain imaging. This is a rock in the Utah desert. This is plants growing on the surface of a puddle down on the canal trail near here. This is a water stain on the floor of the basement in the NIH. And this is a little tiny pothole about this big in the sidewalk at the NIH. The colors have been exaggerated to make them look impressive, but they all kind of look like brains. And this is what happens when you walk around the world, looking at brain images for years on end, is that anything that's kind of like this, brain! And that maybe indicates I've looked at brain images too much. I don't know. But so that is the last slide. So there.
We have time for 2 to 3 questions.
Thank you very much for the presentation. So I like the fact that you stressed that noise is important, and what we call noise and how we model it is particularly critical. And one thing I'm asking or wondering is, in your experience, have you considered, or are you doing any types of effort to reveal that there's a model mismatch in the noise? For example, that you mentioned the autoregressive noise that is probably model or not. Sometimes you can detect that there's a model misfit, and that may prevent people from concluding things that they should not, because it's just a model mismatch. So
we've started doing that in conjunction with this business I mentioned in passing about the treating stimulus effects as random effects rather than fixed effects to estimate. And we have a way of graphing that indicates what happens. And in that process, we discovered that you can get, in an individual stimulus, you can get many, like you have a train of 40 stimuli in one imaging run, say, and that you can get places where the fit is just garbage, and all the other, you have 1 out of 40 are bad, and 39 are decent fits. So we're working on that now, but at the moment we don't have it's not a built-in piece of any package. But the graphs have looked really cool, I can tell you that. That's a good idea, a really good idea. All right, so I guess the next speaker can bring her presentation up. I guess I don't need to take any of this stuff. It's all yours.
Yeah, you can't run off with any of it.